Thank you very much for that introduction and for spoiling my opening joke, which is I'm not one of the signatories of the Agile Manifesto. I'm the first signatory, alphabetically. But it is officially Beck et al., so I'll just enjoy that privately. Oh, so the question mark in the book title, don't ever put punctuation in a book title. If you're thinking about writing a book, it's a really, really bad idea. So just tip. Now you've already learned something. Thank you all very much. No, we have a lot more to talk about. Let me jump right into it. So I'll be live drawing the slides, which I find helps me not talk so fast that no one can understand me. So that seems like a good thing. So software development kind of looks like this. Somebody has an idea for a new thing that the software should do. Then we implement some feature. And part of the magic of software is that everything you implement gives you more ideas for other things that you can implement. So it's not how good it is when it starts, it's how good it becomes over time that creates a lot of value. And if this was all there was to software development, it'd be risky, creative, but straightforward. But we're programmers, and we know that underneath the surface of this lurks the structure of the software. And the structure of the software can dramatically affect how expensive or cheap or quick or long it is to implement the next feature. And sometimes the quickest way to get to the next feature, we have an idea, but it's going to be hard to implement. So the first thing we're going to do is we're going to invest in the structure in some way. There's these two, I have to change 3 different files in order to implement this feature. So the first thing I'm going to do is make it so I only have to change 1 file. That's a change to the structure. User doesn't care how many files, but we care. So I'll change the structure, then I'll implement the feature. And sometimes that's the quickest way to implement the feature. And this is the tidy first flow. So the book is called Tidy First for 2 reasons. One reason is the book I started out to write would have been 8,000 pages. So I cut it down. The cycle's always the same. Oh, I have an idea for writing a book. There's no way I could fill a book with that material. Write. Oh crap, I have 3 books worth of material. So which third do I want to do? Oh wow, that's way too small to fill a book. Right. Oh no, that's another 3 books. Which third of this do I want to? So I boiled, and I'll tell the story in a second about how I got into this. I boiled the first thing I wanted to say about software design to this one moment. You're a programmer, you have to change some code, it's messy. Do you tidy first? That's why the question mark's there. The disappointing, annoying question mark. Do you tidy first? And the answer is probably, but not too much. So there, now you don't have to buy the book. Oh no, I'm going to get into some more here. Don't worry about that. But why? It depends. Where are the trade-offs? And it turns out that you can draw in all the stuff that makes software design so fascinating into that moment of, I need to change this code, it's messy, I can see a way to make it better, should I tidy first? All of the forces that push you to make that structure change or not make that structure change right now are the same forces that looked at in the large influence questions about design changes of very, very large systems. And so I thought, all right, well, we'll start with just this in miniature. And so I started getting into that, and I discovered I could talk about some of the topics that I really wanted to talk about in there. Let me finish this picture, though. Sometimes you implement a feature and you think, oh, that was harder than it should be. We're going to have to implement other stuff there, other stuff like that. So I go from implementing a feature to now investing in the structure a little bit. And last, and this is another part of the magic of software, is sometimes understanding the structure leads you to ideas. You say, somebody says, oh, I wish we could implement da-da-da-da, and you're like, actually, that'd take me about half an hour. What? I thought that would be huge. So this is why product owners can't be the only people making product decisions, because they don't feel the structure under their feet every day the way programmers do. Oops, why is it erasing? Anyway, so this is software development, and lots of people have the intuition that we spend way too little on the structure side. We have tech debt, we can't address it, we try and address it, we get yelled at. That top side above the surface is very visible, very legible. It's easy to count features. But if that's the only thing that we do, we'll soon pile up snow in front of our snowplow and not be able to move. But how is it that we can find a balance between structure and features? And the fact that we've been looking for a sense of balance between structure and features for decades and haven't found it yet suggests that this is a really hard problem. So 3 weeks ago, I've been away from home the whole time, so I have no idea what day it is. I think this is probably Chicago. If it's not, don't disabuse me of that. I was sitting there at GOTO in Copenhagen, listening to Dave Farley's talk about design. And he was saying like 2/3 of what I was going to say in my talk, which is really annoying when it happens before your talk. It's so satisfying when it happens after your talk, because people are like, that guy copied you. You say, well, you know. So it happened before my talk, and my talk was going to be the next day, and I realized, wow, I don't have to say those things. What is it that I would like to say? And so today's talk is about why software design is a hard problem. And there's a set of constraints that make it a difficult problem. This union of the intersection of a set of difficult constraints, and that's what makes it a hard problem. So I'm old enough now to just not be terribly interested in shouting matches about, oh, yeah, but you have to design up front. Oh, but you can't design up front. Like, okay, fine, whatever. You design how you want to design. What I'm going to present is what I see as the constraints on your design style. These are problems you're going to have to resolve one way or another. And then I'll tell you a little bit about how I resolve those. Oh, and then at the end, I have if I have time, I have a little rant about why we don't have to worry about our jobs with AI. So if you'd like to, you like the teaser? Okay. So the first, why is software design a hard problem? Why is it so difficult to get the balance right between investment in structure and investment in feature? Well, annoyingly, yeah, gosh, if only people weren't involved in this, it would be so much simpler. So we have a set of people constraints that make software, like finding that balance, hard. When I sat down to write tidy first, the first words off of my fingers, this is something, as a writer, sometimes your fingers surprise you. Like, I mean, I know that the words have to come out of here at some point, but it doesn't feel that way. First words off of my fingers were, software design is an exercise in human relationships. I thought, what in the hell does that mean? I want to write about coupling and cohesion and power law distributions and all the technical, like, that's where I'm comfortable. Human relationships, not my forte. Like, I work hard at it, but not a natural talent. So what is it about people that constrain software design? The first is it really is about relationships. You know, if you have a relationship with somebody and you say you interrupt them, you didn't know you were doing it, but like you and they're a little bit miffy at you, and then you say, oh, I'm sorry. That's the natural flow of relationships. There's a little strain, there's a little repair, comes together. If there's only ever strain, you get further and further apart. Eventually, it's not worth it. The same thing happens in software design. I have an API, you're calling it, I want to make some design change that's going to affect you. The best case is that I know that it's going to affect you and you know that it's going to affect you. That's the best that can happen. And you're pissed at me, right? That's the best case scenario because you have features to implement. You don't want to update some API call. So if I, as a designer, am going to strain my human relationships, then I, as a designer, also need to be prepared to repair those relationships. You know, and I didn't take that class in college, but there's no excuse, it turns out. Another thing about people that make this difficult is that it's very hard to align authority and responsibility in organizations. Organizations make it easy, if you have power, to misalign authority and responsibility. And by responsibility, I mean the flow of consequences. So if I'm responsible, I make an API change. If I'm going to be responsible for that change, that means that I'm going to bear the consequences to whatever degree I can for that change that I make. I have the authority to make the change. I want to align that with responsibility. That's what keeps those relationships maintained. When the relationships start going downhill, then we start writing up SLAs, pretending like we can legislate getting along, like we can legislate trust. It doesn't work. But commercial organizations really want to separate authority and responsibility. They want to separate responsibility. Oh, bad consequences? That's your problem. Good consequences? I get those. And when we're in that kind of environment, the relationships deteriorate. Everything that's necessary to find that balance between structure and features gets harder and harder and harder over time. And the last thing about the people that make it difficult is just change. The team that are affected, the team that need to have solid relationships, they're going to change over time. The people in those relationships are going to change over time. Somebody that comes in as a junior is going to become a senior. Somebody who was on the technical side will move more to the domain side or vice versa. And whatever we do as designers needs to accommodate the changing needs of the people involved in software design. Second set of constraints. Oh, and by the way, if there are questions, feel free. I'll repeat the question. I'd rather have you ask it than sit there thinking for the rest of the hour. That's what I'd be doing. I'm not saying that's what you'd be doing. Probably. Good so far? Okay. The next set of constraints, and this is something that I don't know, I find people just ignore. I had a comment on LinkedIn recently, which was money affects all software design decisions, unfortunately. I thought, unfortunately? No, I'm delighted. I mean, I need to understand the nature of how money affects software design decisions, but if it doesn't matter economically, then people are going to stop paying me to do it, and then I don't get to do it anymore, and that would be bad. So I'd rather figure out what are those constraints. Last year, I read a book called Ergodicity by Luca Delana that really rewired my brain. So this is actually not in Tidy First, but it's certainly part of my thinking about economics now. The first question is simply one of survival. If your software project doesn't make it till the long term, then every investment you made in that is going to pay off long term doesn't matter. So software design needs to be prepared to increase the chances of the survival of the project first and foremost. Have you heard of loss aversion? This idea that losing $1 hurts more than winning $1 feels good? And people use that as an example of a cognitive bias, like, what, it's the same dollar, come on, man. No, in fact, if you lose $1, you're that much closer to being broke, speaking as a poker player. And so it really is worse to lose $1 than it is good to win $1 because of the fancy word is ergodicity, or the word I use is survival. When you lose, you're that much closer to not being able to play the game at all, which is game over. Okay, so any style of design that you choose that reduces your chances of making it till tomorrow is a mistake if you have any other alternative. Now, this means those messes that we make, that we complain about, that tech debt, if we invested that in survival behavior, that's a good investment. And the fact that we're still there to be wrestling alligators is a good thing, not a bad thing, because the alternative is already being inside of an alligator. So that's one of the factors. Software design should encourage the survival of projects. Another one, and this is, I'm going to try a new illustration of this, and we'll see how this works. And this is net present value. This is a concept I didn't run into, not in college, probably 10 years into programming. And then I had to program the net present value calculation. And I went, I found some definition. I implemented it. I thought, that can't be right. That doesn't make sense. So I played around with it. And I started to develop an intuition. And here's how it goes. You say, oh, it's $1 in. How much is it worth to earn another $1? I can't answer that question until you tell me when. Earning more. If I earn later, that's the same as earning less. Economically, exactly the same as earning less. So, and here's the illustration. If I earn $1,000 today, as I project that out into the future, that $1,000 gets smaller and smaller and smaller. So as designers, when we make software design decisions, is as important or more important than the decisions we make themselves. The same is true of expenses. A big expense today if I can push that into the future, the expense gets smaller and smaller and smaller as I push it out into the future. And now that tech debt, where we were able to cut some corners and book a sale this quarter, starts to make economic sense. We can fuss about it. We can wish that we didn't have to have messes. But economically, it makes sense. I see a lot of advice about software design, the timing, and typically this is, let's do more upfront because it'll save us money later. And that violates net present value. So here, if we have some features, here we have some design decisions, this idea that let's make all these design decisions now, then we'll implement a bunch of features. Okay, so we're going to take our revenue and push it out into the future, and we're going to take our expenses, all this design, and we're going to pull it into the present. So we could say, wouldn't it be nice and tidy if we could just do all the design up front? Well, I mean, there's other reasons why that's a naive idea. There, I said that nicely. But the empirical style is to say, okay, we're going to take those design decisions that we want to make, and we're going to interleave them with features that we implement. And this is part of why I'm not interested in having the design upfront debate, because this or this, who cares? It's just not a big deal. But we would like a style of software design that pushes expenses into the future and draws revenue closer, if we can. And then the third economic factor is optionality. Yes, I stayed on the projector, good. And this is, so imagine we have a software system and it brings in $1 million a year, and we have another software, but we can't change it. We have another software system that brings in $1 million a year, but we could do this with it, or that with it, or that with it, or that with it. Which one are we going to pay more for? The one with all the options. And this is, now the picture started coming more clear in my head. Why do we invest in structure? To create optionality. Like, why do we design at all? Computer doesn't care. Computer doesn't care if the variables are named consistently. Computer doesn't care if we have one gigantic main program or lots of really beautiful little pieces that all work together. We design for change. So any design investment that we make should be enabling change in the future. And net present value and optionality can conflict. So if we say, all right, well, we're going to do a little design, we'll implement a feature. Should we design next or should we implement the feature next? Well, the feature should improve cash flow in some way. So we would like to do that. But we would also like the optionality to do 3 different things. If we do the design, we'll have more options. And so this is a genuine judgment call. Oh, and by the way, the information necessary to rationally make these decisions doesn't exist at the moment you make the decision. So that's why we rely on gut feel, on collaboration, and on a set of principles. So those are the money things that make software development or software design difficult. Now, there are some aspects of software that also make software design difficult, finding this balance between structure and features. The first is what I call Constantine's equivalence. Larry Constantine and Ed Jordan in 1980 published a book called Structured Design. Green book. Anybody here read it? Yeah. It was the book that introduced the terms coupling and cohesion. And in 2005, I was invited to be on an Uppsala panel to discuss the book and its 25th anniversary. And Ed, who's since passed, and Larry were going to be on the panel. So I thought, you know, I had this book as a textbook in college. I should probably read it. So I started reading this book, and I was gobsmacked. Here are Newton's laws of motion for software design. Clearly laid out, clear concepts, clear language, and examples, paper tape readers, punch cards, big debate about assembly language versus these newfangled higher level languages. Does anybody really want them? So buried under these dated examples were the laws that really affect software development. And I said, 2005, I said, I'm going to bring this material into today. It took me 18 years so far, and I'm not done yet. But that's neither here nor there. One of the observations in there, and what I call Constantine's equivalence, is, and their point of view is that the goal of software is the goal of design is to reduce the cost of software. Now, I think adding revenue to the equation is important, but that was their perspective. So what is the cost of software? The cost of software is primarily the cost of changing the software, not that upfront, whatever happens before we go into production. If the project is successful, that cost is going to be dwarfed by all of the expenses that we've incurred afterwards. So the cost of software is approximately equal to the cost of changing. So let's think about how we can reduce the cost of changing the software, not reduce the cost of putting it into production in the first place, because who cares? But all changes aren't the same. And this is another part of the genius of this book. Some changes are easy, and we've all been through this. Somebody asks for a feature, you say, oh, it'll take a week. Here's another feature, that'll take a week. Here's another feature, that'll take 8 months. 8 months? What? Why? Well, it's just true. I need it in a week, because features take a week. What's wrong with you? Now, maybe your boss doesn't talk to you that way, but it's happened to me maybe. Those big changes, if you add up the big changes, they add up, even though there's not so many big changes, but if you add up all those costs, it dwarfs the cost of all of the little changes that we make. So if we want to reduce the cost of software, we need to figure out those jackpots. How does that happen? How can we reduce the probability and the expense of those big changes? And we'll reduce the overall cost of software. So the cost of software is the cost of change. The cost of change is approximately the cost of big changes. And how do those big changes come about? It's because of coupling. Their definition of coupling is different than kind of the folk, lay, informal definition. Coupling has come to mean like there's two things and they're related. The original definition of coupling, which is the one that I use now, is much more specific. It says, if I change this, I have to change that. If that's true, then those two elements are coupled. So if I have a function, it calls another function. Those are coupled with respect to changes of the name of the called function. Because if I change the name of the called function, I have to go to find all the callers and change all of those. That's what coupling is. It's two elements and a change. There can be potential coupling that it's like potential energy. You just never trip over it, so it doesn't really happen. Well, if I ever change this, I'm going to have to change 1,000 of those things, but I never have to change this. Okay. So that definition of coupling then drives these big changes, because I change this, which means I have to change 4 of those, which means I have to change 18 other things. One of those changes causes a bug, which causes a production problem, which forces me to roll back some and change some more, and now we have one of those big jackpot changes. Like, if you're lucky, you'll notice that this feature is not like those last 2. That's the best case scenario, is that we deliver really horrible news. Like right on the date. And in fact, this month, I published my 11th book. It's a very short book. It's a executive briefing. It's the first time I've tried to talk to a non-technical audience on purpose. Sometimes it happens, and it's always a shock, but it's called The Good News Factory. And it's why would you go to the trouble of understanding and managing this balance between structure and behavior from an executive's perspective? What would it be like if software development regularly delivered good news, instead of just being this endless fountain of no, worse than that, disaster, no, that we're all trapped in. So, but managing coupling is not for free. You can't eliminate coupling. If you eliminated all coupling in one dimension, you're going to create coupling in another dimension. And decoupling is not free. So we're in this trade-off space. You know the international symbol for trade-off space? I made it up. And then I just came back from Portugal, so it's international. Never mind. So coupling costs. The more coupling you have in your system, the more those features are going to cost, the more likely you're going to have one of those big changes that goes spread, like a virus, exactly like a virus. But we also have cost for decoupling. If we go and do a bunch of refactoring, that takes money away that we could have been spending on other stuff. So you have to find this valley of reasonable investment someplace in between trying to decouple all the things, which is impossible, and just paying for all of the coupling and thinking that it must be our fault. And if we were better programmers and wore smaller clothes, then everything would be fine. Let's see, 20 minutes. Okay, I'm just going to mention this because it's so much fun for me, and that is power law distributions. Pareto's law is this similar kind of thing. They're everywhere in software. And I've been collecting them for probably 25 years. And every time I find a new one, I get so excited. And that's what coupling causes. And it is exactly a natural process like avalanches. You know, most avalanches is one snowflake going clook. And that's it. Except if that snowflake knocks over 2 other snowflakes. And each of those knocks over 2 other snowflakes, and the village goes down to the bottom of the valley. So in software, we're managing a natural process. We don't actually have full control. So something like, what's the distribution of the number of parameters per function? There's lots of functions that have 0 parameters. Half that many have 1 parameter. Half that many have 2. Half that many have 4. Half that many have 8. And there'll be one function with 128 parameters, and that's fine, as long as it's on that distribution. Because then if we take these, I got started. I shouldn't have gotten started. I knew that. If we change the axes to logarithmic, 110, 100,000, 110, 100,000, we get a straight line every time. It's so cool. Also, power law distributions don't obey the law of large numbers. So if anybody asks you, well, the average number, or tells you the average number of function parameters should be 6, no. The bigger the system is, the larger the average should be. The mean doesn't tell you anything in a power law distribution. Anyway, I promised I wouldn't get into it, and then I got into it. Okay, so this is my picture that I came up with in Dave Farley's talk for why software design is hard, for why balancing investment in structure and with investment in features is really hard to do, because it comes at this intersection of people constraints, financial constraints, and software is this unique material. And this is what I call empirical software design. Something that happens at the junction of all of those. Now, you're welcome to ignore some of these constraints. If it's just it's too much for me, I don't want to deal with that. I just want to design everything up front. Whatever, that's fine, but the constraints aren't going to ignore you. These will be affecting your life as somebody making decisions about software design. Okay, so a little bit about consequences. So one consequence, if I took those constraints seriously and I said, how do I want to design software? First consequence is that I'm going to design like a tree grows. I'm going to start with something small and then split it. And then maybe split one of those things. And then maybe split another thing. And if I make a mistake, if I have one thing and I split it and now I have to change both of them at the same time, that's coupling. Now, maybe it's the right thing to do at the moment, but I have introduced coupling at that moment. So as a designer, you have 3 basic moves. One is differentiation. I have an element and I split it. I have a function and I extract a helper function. I have a service and I split it into 2 services. Differentiation. Another is unification, where I notice, through this process of differentiation now, this and this are exactly the same. Well, let me unify those 2 so I only have one element, and I eliminate coupling when I do that, which increases optionality. Or I have 2 things and they're almost the same, but they're a little bit different. So I'm going to differentiate the parts that are identical from the parts that are different, and then I'm going to unify the parts that are identical. So we have differentiation, unification, and deletion. I say, this isn't used, or more likely, this almost isn't used. So now I'm going to go back and do the prep work so that this isn't used at all, and then I can delete it. So we'll grow like a tree grows, which means that software design is an activity and not anything like a phase. We're going to be investing in the optionality of the software as long as it exists. And this is back to Extreme Programming 101, where we had this big waterfall. And the waterfall's back. Have you noticed that? Like, genuinely smart people are saying genuinely naive things. There, I said it nicely again. Where it had these phases, except now they will do a thorough market research. Then the designers will put the wireframes together, and then there's some annoying programmer implementation stuff. And then no testing. We just release it at that point. That's the Neo Waterfall Manifesto right there. I'm the sole author. Oh, God. Somebody that's going to probably... Anyway. So in extreme programming, we just take those phases that never really were phases. Read the original waterfall paper sometime, just for laughs and to cry. Those phases just become activities. We're going to be spending some time on software design as long as the software exists, as long as we want to change it. If it ever doesn't need to be changed, then we better not be designing it. But until that day, we should be designing it. If software design is an activity, though, then the changes should be interruptible. So if I have, here's the old design, here's the design I want to move to, I should be able to make that change in slices. Oh, here's the big design change I want to make. I should be able to make that design change in slices and continue delivering features while I do it. It's messy, it's hard. If it was easy, regular people would do it. So it does mean, I have a cute story about eating an entire sausage in little slices. There, that's the setup. If you have n slices of salami, you have n factorial ways of eating the slices. You can order the slices any way you want. So part of the new skill, the empirical skill of software design, is making thinner slices and getting more creative about what order I'm going to do the slices in so that I can maintain this heartbeat of features at the same time. Oh, we could make that design change, but it's going to take 6 months. Okay, take 18 months. And interleave features, but choose the pieces of the design that you want to do so that I realize value sooner, because net present value. If I draw it in closer, the value gets bigger. That's part of the skill that I'm talking about. The technical skill of that is what I call parallels. And this is having the old design and the new design coexist at the same time, which is a pain. Okay, we have this service, it's not scaling, we need to replace it with a service that will scale. We're going to run both of those services at the same time for a while. Oh yeah, but then we have to sync data, blah, 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 blah. Okay? That's the price that we pay for being empirical in software design. And then the last consequence I'm going to talk about right now is this structure feature split. From up in an airplane and we're looking down at the software development, it looks like we're designing and implementing features at the same time, always. Now, sometimes the proportions adjust this way and that, and features may be coming slower for a while, but then they speed up. But from a macro view, we're always seeing progress on both fronts. But the way to achieve that is to have absolute separation at the lowest level. So no commit can have both structure changes and behavior changes in it. As a designer, and everybody's making some design decisions in this style, as somebody making design decisions, let's say we go program for an hour and we add some if statements, and then we change some names of some variables, and we extract some helpers, and we da-da-da. Okay, that's fine, except now the work's not done. We may think, oh, I could put this in production. No. I mean, go back and sort it out so that here I'm going to make these structure changes, And then I'm going to make these behavior changes, and I'm going to keep them separate. And that becomes a habit. And that's back to this tidy first mentality where you say, I'd like to make this change. It's harder than it needs to be. I'm going to make the change easy, then make the easy change. So these are just my conclusions. This is my understanding of the consequences of software design, and this balance between structure and features is really hard because it's really hard. We're trying to satisfy a very difficult set of constraints. Those are the constraints that I showed you earlier, and these are the consequences that flow from those constraints for my style of software design. Now, wherever you take that, up to you. Questions about that? I know you're waiting for that AI rant. Yes, go ahead.
It's that structure feature split on the commit level. For like your review, structure split makes total sense, right? I get it. But beyond that, like what's the, if I'm assuming I'm doing a unit test, everything's perfect, right? What's the logic for why that needs to be separate?
What's the logic for why it needs to be separate? Great question. Try it both ways. I evolved to this style where I only change structure or change behavior and never both at the same time. I think it's a form of complexity management. So my brain is a finite size, and if I'm trying to change two things at once and do a good job of both of them, I just can't do it. And so I roll that back and say, all right, let me just do one of these. Sometimes I just slap in a feature and it's ugly and that's fine, and then I change the structure. That's the tidy afterflow. Sometimes I change the structure and then I say, oh, now the feature is easy to implement. So I think it's yes. I've convinced myself in real time that that's why I do that. Yeah. Yes, ma'am.
I'm not sure this works. I had the same question, and I have also a potential answer. Particularly when you work with a team, if you do the structure changes, then the team can focus on what is the actual change in the structure and better give you input and feedback, perhaps.
Yes, absolutely. And structure changes tend to be reversible. So if I extract a helper and you're like, that's not the right helper to extract, you just inline it and we're finished. If I change the behavior in some way and now we send a bunch of reports to the tax authorities and whoopsie, that's not easily reversible. So the teams I work on, structure changes are for free. There's no review. Just if you think the structure is improved by this, go ahead and do it. So that's another part of the logic behind, or thinking behind it. Okay, AI rant, short version. If we're spending too much electricity on electric lights and we make light bulbs more efficient, will we spend less electricity or more electricity? More, yes, exactly. And why? William Jevons was this thinker, one of those rich British guys who just had nothing better to do than to think. And he noticed that at some point, England was running out of coal because the steam engine had come in and more steam engines meant more coal, and they were going to use up all the coal in England. And then, so they made steam engines more efficient. And consumption of coal increased. This is called Jevons paradox. Why did it increase? Because now there's many more economic uses for a steam engine. If they're cheaper to operate, now we can use a bunch more of them. Same goes with the electric lights. If electric lights are cheaper, we're like, okay, we'll put them up here and there and everywhere, and now we're going to use more electricity. So this is a fun party trick if somebody says, oh, I'm making this more efficient, so there's some critical resource that's I'm not going to use as much of. You can just calmly make the prediction, no, this is going to make the problem worse, but go ahead. And what happened in England was a big use of steam engines was pumping water out of coal mines. So now they pumped a lot more water out of a lot more coal mines. Now they produce more coal. So the fact that they were consuming more coal wasn't a big problem. That's my argument for why AI is not going to take programmer jobs. We're just going to, there's some margin where we say, it's just not worth programmer time to solve this problem with a custom program. And that margin is going to expand, which means that jobs for people who think like programmers are going to expand. That's why I'm personally not worried about it. Now, I looked it up today, and it turns out that 50 years ago, there were 400,000 telephone operators in America, and now there are less than 4,000. So I could be completely wrong about this. But I'm going to choose to be positive about it. And at my stage of career, it's not going to be my problem. So thank you all so much for your time.